Ladies and gentlemen, this is Mr. Witt with Fort Bend Tutoring, and today's tutorial is going to be about solving exponential equations. And first of all, we want to thank MamaGena and the East Texas Homeschool Collective for the Afrocentric child. And we want to say what up to Gage. What's up, Gage? This video is for you, brother. So hopefully this helps you out along your academic journey, sir. And we're going to go ahead and get started. That's right. Let's go ahead and get started with problem number one. We have 4 to the x equals 64. So when you have a problem like this, you can, if possible, make both sides of the equation have the exact same base. So what do I mean by that? Let's say that b represents your base on each side of the equation. If you have b to the m equal to b to the n, Gage, then in a situation like this, m would be equal to n in that scenario. That's right. So as long as we can get the exact same base on either side of the equation raised to an exponent, then the exponents, because of that equal sign, they have to be the same, Gage. It is what it is. So in our equation here, we can rewrite the right side as 64 being equivalent to 4 to the third power. So now that we have each term on either side of the equation have a base of 4, then the exponents must be the same. So therefore, we can say that x must be equal to 3. And this is our answer right here. Okay, and what we're going to do with that, Gage, is we're going to red box our answer just like that. Here we go. Here we go. We're going to get it together. Don't get it together, Gage. And there you have x being equal to 3, and that is a done deal. You can always plug your result back into the original equation to see if it equals to one another. In other words, if 4 is raised to the third power, does that equal to 64? Well, yes, it does, Gage, because 4 times 4 times 4 equals to 64, because as you see here, 4 times 4 is 16, and then 16 times 4 is 64, just like that. All right, so it checks out. We got a check mark right there. All right, let's move on to our next problem, problem number 2. All right, we got problem number 2 next. Let's check that out, guys. Here we go. Lining everything up. We have 1/3 raised to the x equals 27. And just as I said in the previous problem, if you're able to set the terms on both sides of the equation to have the same base, that is a winning formula for solving exponential equations. As you see the base on the left side is 1/3, we could rewrite this, Gage, by rewriting it as 3 to the negative first power raised to the x, while this still equals to 27. And then because the exponents will multiply when they're set up like that on the left side, we can say that this is 3 to the negative x equals 27, just like that. From here, Gage, we can say that 27 is equivalent to 3 to the third power. Once again, we have the opportunity to write each term on either side of the equation with a base of 3, that common base. Remember, we said that if b to the m equals to b to the n, then in that case, m would be equal to n. So that's what I'm looking to do in this equation right here, Gage. So notice that since we have those bases equal to 3, we can then say that negative x must be equal to 3. And then, of course, solving for x, you'll want to divide both sides or multiply both sides by -1, and x equals -3. And we got a red box waiting for you, Gage, right there, and done. Yeah, that's it. That's problem example 2. All right. So make sure that if you have any questions, you reach back to MamaGena, Gage, and you go ahead and let her know that if you have some questions, I can go ahead and try to clear those up for you. All right. That was problem number 2. Problem number 3 we have here, sir. And with problem number 3, let's go ahead and line it up over here on the iPad, Gage. We're going to say the following. We're going to have the 5 to the 2x minus 1 equals 17. Now, this is the first time, Gage, that you've seen a situation like this where we do not have the opportunity to make a common base. That 5 is nowhere ever going to become a common base with 17 and vice versa. So what you can do is you can use either the natural logarithm or the common logarithm. And to fill you in on what I'm talking about is the common logarithm, let's go ahead and write that out, is when you have log x, let's say, all right? And that is equivalent to log base 10. So your common logarithm has a base of 10, whereas your natural logarithm, all right, so when you have it like this, so the symbolism for that is the natural log of x, they write it like that, and then Written out as a regular logarithm, the base would be the natural number, or e, okay? Where e is called Euler's number, is called the natural number, and that's how you get that term, natural logarithm. So I prefer to use natural logarithms. Not that I have to, Gage, it's just that it's the one less letter to write. So I'm going to rewrite this problem as, let's see here, let me see here. I'm going to rewrite it as the natural log of 5 raised to the 2x minus 1, which equals to the natural log of 17. And because I'm using what is called the power rule allows us to bring down this exponent here, this 2x minus 1. It'll allow me to bring that down as a coefficient. So I'll be able to rewrite this as the quantity 2x minus 1 times the natural log of 5. Just like that, Gage. All right. And then what I can do next is I can divide both sides by the natural log of 5. So let's try that out. So dividing both sides by the natural log of 5, we have this, okay? Then on the left side, the natural logs will cancel out. So I'm left now with 2x minus 1 equals to the natural log of 17 divided by the natural log of 15. From here, Gage, I'm going to go ahead and add 1 to both sides of the equation, like so. Just like this, line it up. And my 2x comes down. Of course, the 1s will cancel out here. We'll bring down that natural log of 17 divided by the natural log of 15 plus 1. And then what we can do is we can multiply both sides by 1/2, which is the reciprocal of the 2. You could also say you can divide it by 2, but it won't look as cute. So if we go ahead and say I'm multiplying both sides by 1/2, Gage, then you'll end up with a scenario like this. Go ahead and show you how this looks, sir. Just like this here. Matter of fact, you'll probably want to keep all of that inside the parentheses like that, right? So on the left side, what happens is the 2's will cancel out, and now you have your variable x, just like this. And you end up with your answer, which is just 1/2, right, times the quantity of the natural log of 17 divided by the natural log of 15 plus 1, just like that. Okay. Now you could put this in the calculator because see, right now you have what is called the exact answer. All right. And because many of your answers are irrational numbers when you're dealing with natural logarithms, or just really small or really big numbers, you're going to need a calculator for that part. So a lot of times they'll take this answer as it is. But if you do need to put it in the calculator, let me show you what that looks like. All right, so using our calculator here, Gage, let's go ahead and say that we have exactly what we see thus far, which is going to be 1/2. Go ahead and type this in, sir. Just like that. Okay, let's get some parentheses in there. Let's go ahead and put in our fraction because in the numerator we are saying that we have the natural logarithm, all right, of 17, and that's divided by the natural logarithm of 15, okay? And then outside of that, we're going to say that we have plus 1. All right, let's go ahead and see what this equals then. All right, they give me the exact result, but I need the approximation. So here we go. So now that we have that, sir, we end up with a result of 1 and 231 10,000ths. All right, so that's the answer if you were to go out to the 10,000ths place, Gage, just like that. So you have your exact answer and you have your approximation using a calculator. So notice that you had to use your calculator to get an approximation of the exact result. All right, so there you go. All right, so there we have it. And that was problem number 3, sir. Problem number 3. And now what we're going to be looking to do is our next problem, right? Let's get the next problem going. Let's get this next problem going over here, Gage. Let's check it out. We got problem example 4 now. Now, with problem example 4, you have Euler's number as the base. You have that e value. You have that natural number, right? And it's e to the 3x equals 21. So once again, my preference is to use natural logarithms. But I will also tell you this, is that there is a rule that says that if you're taking the natural log of e raised to a value, raised to a number, we'll call that number u, that the result here is u. So in other words, the natural log and the e, they will cancel out to give you the exponent. So I'm going to take the natural logarithm of both sides of the equation, like so. And I'm going to end up being able to cancel out that natural log and e. I'm bringing down the 3x, which now equals to the natural log of 21, and then I'll divide both sides by 3. You could multiply both sides by 1/3, sir. That is an option, Gage, if you wanted to do that. Or you can just bring it down as is. So I'm going to write it as 1/3 the natural log of 21. And that's going to be my result here. You could use the power rule on that gauge, and you could say that you have the natural log of 21 raised to the 1/3 power. You could even write it as the natural log of the cube root of 21. Or you can find out what that actual answer is. So let's see what that looks like, sir. If we say that we're taking the natural log of the cube root, where will that be? All right, so we're going to say that we got the cube root of 21. That's another way of saying it, right? Let's go ahead and get that result. All right, so give me that. It gives me that. Or just to let you know that you could get the answer the other way, written the other way before we did the power rule. Let's see what that looks like, H. Huh? Let's see what that looks like. We'll have 1/3. This is going to be the natural log of 21. Yeah? Yeah? Let's go ahead and hit that enter on that. Same value. See what I'm saying? So you can write it either way and get the results. All right, so let's go ahead and write this out to the 10,000ths place. We'll have 1 and 148 10,000ths. I hate the 8 gauge. There we go, much better. And then you can red box this. So once again, any one of these versions here, you can call the answer. That is right. You got the exact answer, and then you got the approximation at the end where we're rounding it out. Okay? So I don't know about that one in the middle. I mean, it's fine, but I like it. I like the ones, the 3 in the boxes. I like those, Gage. All right, I like those a lot. So that was example 4, sir. That was example 4. There you go. Shout out again to MamaGena, guys. Let's go ahead and move on to problem number 5, shall we? Here we go. So we have problem number 5. Now on your screen it says solve for x gauge, but trust me, we need to be solving for t. All right. So what I have on my iPad is absolutely correct, sir. And we have 90 equals to 50 e to the 1200s t. And what we're going to be doing in this problem first is isolating the base with a natural number. That's right, Euler's number, Gauge. So we're going to start out by dividing both sides by 50. Let's get it. Right? So dividing both sides by 50. We'll now have 90 50ths equals e to the 1200s t, just like that. And I'm going to go ahead and want to simplify this. If you notice on the left side, Gauge, that 90 50ths can both be reduced by 10, right? So let's go ahead and reduce that to 9/5 equals e to the 1200s t. From here, what we can do is use the natural logarithm to go ahead and get rid of Euler's number and bring that exponent down on the right side. So I'm going to have the natural log of 9/5 equals the natural log of e to the 1200s t. And what happens on the right side, in this case, Gauge, is the natural log, and the e will cancel out. And you'll be able to bring down that 1200s t, which equals to the natural log of 9/5, just like that. Then what we can do with this is that 1200s, I don't like that fraction, to be honest with you. So let's go ahead and change this to what? This is what, 1200s t. We can reduce both of these by what, 4? So you get 3/25ths t. Yeah, that's better, right? So you'll have the natural log of 9/5, like so, equals 3/25ths t. And then we can multiply both sides by the reciprocal, which is going to be 25/3. So we have 25/3 times the natural log of 9/5, and this equals to 25/3 times 3/25ths t, like so, Gauge. On the right side, all that cancels out except for the variable t. Matter of fact, I'm going to write that t first now. I'm going to say that we have 25 times the natural log of 9/5 all over 3. There you go. So you could write it like that, Gauge, okay? And that would be fine. That would be the right answer. So you can write it like that, or I guess you could say that you added 25/3 times the natural log of 9/5. You could write it like that too, or we can get that decimal answer using the calculator. So let's look at that. We'll have let's get here. Got a fraction up in there, Gauge. We got 25/3. Get that going. And there's going to be times the natural log, yes sir, of 9/5. I need to get a fraction now, okay? So we got 9/5. Yes, sir. And then let's go ahead and approximate that. There we go. We end up with 4 and rounding out to the 10,000s place, 8,982 10,000s, guys, just like that. I'm gonna put a red box around this answer. So that's my approximation, whereas these other two versions are the exact answer. Once again, depends on the worksheet or the assignment or your teacher, what version they'll want to write that in. So I'm letting you know, sir, that concludes your introduction to this topic, sir. Once again, this was solving exponential equations. I gave you several methods to look at the problems. And once again, this is Mr. Witt with Fort Bend Tutoring and telling everybody out there, all right, peace. Take care.